Okay, so today we are looking at the absolute area bounded by a graph and the x-axis, and what that means to find the total volume or the total area that would be covered by such an idea. Now, when we work through the sigma notation and we find these sums, what the sum is doing is it's looking at, let's say we have a graph that looks like this. I have two areas. If I'm bounding it from 0 to 7, and it's between the graph and the x-axis, I have several areas above the axis and areas below the axis. What summation notation will do is it will take all of these areas and find their net input. It basically takes what was above and pushes it down into below, and it says, hey, I took that entire amount and filled this up, therefore it's a negative value. It doesn't compute what the total area would be of this plus this if we're finding the area bounded. Now, for some cases, like with construction, this is really good because it tells you how much do you need to ship in or how much do you need to ship out, and it'll work out. But for us, what we're going to eventually be doing is we're going to be taking these shapes and we're going to spin them to create three-dimensional shapes to find volume. And so I want to find the total area covered by this graph, not in a net area, but total area. So we're going to look at that as a series of absolutes. So to further highlight that, let's take a look at the first question. Now the first question right here, I've got this graph and I'm bounding it from 0 to 10. So I think the best way to start this is let's take a look at this graph and bound it from 0 to 10. So I have a negative, x plus 2, x plus 3. And let's take a look at the window from 0 to 10 and see where, okay, so it's way down there. Hold on, did I get that right? No, minus 3. There we go. So what I see is the graph. I might want to make that y min. Let's make that negative 50. Closer. Let's do that negative 75. Negative 100. Okay, so what we've got going on here is we now see that I will have a small amount of positive area and I will have a large amount of negative area. So if I were to try and use sigma notation on this, I would get a large negative result and I would not account for this. I would actually get a number that's smaller than what I want because all of this area would be taken away from this and I would only be finding the area of, let's say, this part of the graph because these two areas would completely cancel out. So that's not the appropriate area that we want to find. I want to find the total area, which means I'm going to first have to find this point, and instead of finding it from 0 to 10, find my area from here to here, calculate that, and then find my area from here to 10 and calculate this, and add the two values together in absolute terms. So I'd find the absolute area, which is already positive, the absolute area, which would be negative, and add them together. So let's go ahead and set that up. So for the first one, let's take a look. I know this area is going to end up being 250.3 roughly. Okay, so at that point, I know that I will have an intercept at 3. So this is going to turn it into two problems where I have it from not 0 to 10, but from 0 to 3. And then again, from 3 to 10. Okay, so I could work this problem twice and work it f of x is this from 0 to 3 on the left side and then do the same thing again from 3 to 10 over here on the right side. And that's a valid way to work the question. I, however, don't want to work the same thing twice. So what I'm going to do is I'm going to try and work this equation abstractly using instead of a 0 and a 3 and then a 3 and a 10, I'm going to work this using from A to B. The first thing I'll need to do is simplify what's here on the left. So what's on the left, I'm going to simplify this down to a negative, let's see, FOIL that, x squared minus 2x, plus 2 minus 3 minus 6, which is going to be a negative x squared plus x plus 6. Awesome. So I'm finding the area bounded by this from A to B. So let's use our limit, and let's zoom in just a little bit as we work through this. Okay, so I want to find the limit as my number of rectangles is approaching infinity of the sum of all of those rectangles from the first rectangle to the last rectangle of this. So it's going to be base times height. Okay? And then we're going to simplify what this base is here throughout this. So my base, we know, is going to be delta x. And so my delta x, if I come over here, is usually my endpoint minus my start point divided by the number of rectangles. And normally I would have numbers and I'd plug those in and simplify it, but in this case, I can't. So I'm going to leave it as a delta x. My height can. So let's take my height. Now again, because I'm using the limit as n approaches infinity, I'm going to take that right end rule. So a plus delta x I. I'm plugging that in. Okay. So this is going to give me negative a plus delta xi squared plus a plus delta xi singularly plus 6. Okay. Still times my delta x. Okay. The next thing we're going to do is I'm going to FOIL this. So I leave my negative. That's going to give me an a squared plus 2a delta xi plus delta x squared I squared. The parentheses can just drop off, so I have a delta xi plus 6. Again, times delta x. Now what I realistically could be doing, again, is if I wanted to solve this with the 0 and the 3 first, I could be doing this math once with this, and then once again over here with these two values. We're solving this abstractly so that I'm going to solve this once all the way down. Then I can plug in my A and my B. The reason why is because I only have 2 areas. If this function did an oscillation several times, I really want to do it this way because that will save me a lot of work in the long run. With 2, it's probably going to be about the same. But let's keep going on this. Distribute my negative in there. So negative a squared minus 2a delta xi. Nope, not a plus. That is a minus delta x squared I squared plus a plus delta xi plus 6. Okay, and then I have my delta x. Now at this point I can either distribute the delta x in, which might be the best idea. So let's go ahead and distribute the delta x in. So I have a negative a squared delta x minus 2a delta x squared I minus delta x cubed I squared plus a delta x squared I 6 delta x. And now this is a lot going on. So what I probably want to do is I know eventually I'm going to try and separate out the I squareds, the i's, and then the constants. So let's go ahead and combine the terms that we can where we can. So my I squared I'm going to go for first. I have that. My i's I'm going to do second, so I'm going to combine this and this, and those are the only 2 terms where I have an I. Double check, yep. Those are the only 2 terms I have an I. And then everything else is going to be a constant because they have no I values in there. So if I move my I squared term to the front, that's going to be a negative delta x cubed I squared. I'm going to remove the coefficients from that. Next, I'm going to move these two terms together. And because I can't add their values, because again, I haven't plugged in an A and a B yet, I want to work this abstractly, I'm going to remove their coefficients. So this is going to be plus negative 2a delta x squared plus delta x squared I. So I just took their coefficients and combined them right there. Lastly, these are just three individual terms. There's no i's, so I'm going to combine them however we can. I have an a squared, an a, and a 6, so I'm just going to leave that as negative a squared delta x plus a delta x plus 6 delta x. So I have my I squared, my I, and my regular thing. Now, that is the important part because what we want to do at this point is find the sum from 1 to n. So I'm going to keep my coefficients, negative delta x cubed, and I'm going to plug in the formula for I squared. So this is my last stage where I still have my sigma notation. After this point, my sigma notation drops off because I'm about to plug in the formulas. My limit is still there. I have not yet plugged that in. Okay, let's go ahead and plug in the sigma notation. So I squared is going to be n times n plus 1 times 2n plus 1 divided by 6. For this one, I'll still have our negative 2a delta x squared plus delta x squared times the summation formula for I, which is going to be n times n plus 1 all over 2. And then I'll have the summation formula for this one, which is going to be times n. So plus negative a squared delta x plus a delta x plus 6 delta x times n. Okay. Now I could work this out, but I think this is a good stopping point to go ahead and plug in our a's and our b's, because at this point I'm going to try and combine these as best I can. I could work this abstractly a little bit longer, but I think we're going to have a little better set of circumstances if we work this out as the two separate problems. So I'm going to say that this is now just my limit. Okay. And boom. So for the first one, we said that we were going to be doing this from 0 to 3. So for the first set, I'm going to split this up into 2. Zero to 3. And for the right one, I'm going to do it from 3 to 10. Okay. So in this case, I know that my A is going to be 0 and my B is going to be 3. And in this case, my delta x is going to be 3 minus 0 over n. And so I'm going to plug in all of those values into this. Okay. So I have a negative delta x cubed. So that's going to be a negative 3 cubed is 27 over n cubed. In this case, I'm going to keep the n out here and I'm going to FOIL this. So n times 2n squared plus 3n plus 1. In this case, when I go to plug in my a, I know my first term right here, because it's times a, is going to completely cancel out. So I'm only dealing with the delta x squared. So this is going to be 0 plus delta x squared, which is going to be 9 over n squared. And again, I'm going to leave this separate, and you'll see why in just a moment. Okay, so I probably should have left a little more space or wrote in a little smaller. But I notice, again, if my a term cancels, I'm only dealing with 6 times delta x times n. So I'm going to put 0, 0, 6 times delta x, which is 6 times 3n, 18 over n, times n. Okay? Now at this stage, we're going to simplify and try and do what we've done previously where we combine them all into one thing. Okay, so where can I start eliminating? So I notice n is going to cancel out here and leave me with an n squared. Same over here. N is going to cancel out and leave me with an n, and the n's completely cancel out over here. I'm going to distribute that negative 27 into this. This will give me a negative 54n squared. 27 times 3, that's going to give me, make sure my arithmetic is good, negative 81n minus 27 all over 6n squared. Those two n's cancel out. I have 9n plus 9 all over 2n. And this I have plus 18. I'm still taking the limit as n approaches infinity, so I should double up and write that. Limit as n is approaching infinity is still taken right here. Now I want to combine these three things into one fraction, which means I need them all to be over 6n squared, which means I'm going to work in this case, 3n, in this case, a 6n squared. This will allow me to combine all three. I'll have a negative 54n squared minus 81n. That's going to be 27. So 18 times 6 is going to give me 108. All divided by 6n squared. And we know that at this point we're going to combine our squared terms first. Squared, squared, squared. I'll combine our n terms second. And then our constants third. We know that at this point the way this plays out is that I'm going to have my n's and my constants are going to have the n squared on bottom. So mostly what I'm paying attention to is my n squared here, because that's the important part. So I have 27 plus 108 minus 54. And I'm left with 81 n squared over 6n squared. 27 minus 81 minus 54 n over n squared minus 27 over. Awesome. And so at this point is where we impose the limit. So when I impose the limit and I plug in the infinity in the bottom, actually before we even do that, these n squareds cancel out n and nothing. So I know that with the infinity in the bottom, I'm going to have 54 divided by infinity, 27 divided by an even bigger infinity. I know that these are going to completely wipe out. So I do have to show this as one more step. 81 over 6 minus 54 over 6, 27 over 6. Which when I plug in that infinity, cancels. It's 81 over 6. In this case, 81 divided by 6 is roughly 13.5. That is the sum of the area that we had. If I look at that 13.5, and I look at the graph, that area up here is 13.5. when I do this area on the right, I'll figure out what this area is. So let's do that. Okay. Now this one, because I didn't have enough lateral space right here, I'm going to put all of this right across the top. So this means A is 3, and B is 10, and delta x, 10 minus 3 is going to be 7 over n. Let's work that out. Now, unfortunately, because the A doesn't cancel out, I do need to plug in every one of these terms. So let's just get a rolling. I have yet to impose the limit. So I write out the limit notation. And I have negative delta x cubed. So 7 cubed, 7 by 7 by 7, I believe is 343. Let me double check. 7 to the power of 3 is 343. So 343 over n cubed times this purple thing. And then I plug in my other values right here. Let's see, so this is 2 times A, so 2 times this is going to give me a negative 6, but we're going to write this out. Nah, we don't have enough space, so negative 2 times 3 is negative 6, times delta x squared, so this is going to be times 49 over n squared, plus delta x squared, so plus 49 over n squared times this thing. And then we're moving on to the third aspect. Negative a squared, so in this case it's going to be negative 9 times delta x, so times 7 over n, plus a times delta x, so 3 times that, so 21, plus 6 times delta x, so plus 42, times n. Kind of using up all our available space here. Okay, that was a little longer, but again, it's just we gotta combine this using arithmetic and algebra. Okay. The first thing that I notice is that my n cubed and my n are going to cancel out on that first term and leave me with an n squared. The next thing I notice is these are both over an n squared, which means they have a common denominator. I can cancel out one of those n's with one of the top ends. Same thing over here, they're all over n, which means this n can cancel out each one of those. And then I go through and I see, what can I reduce? Oh, that 343 is a 7 cubed, so I can't reduce that. So I gotta figure out what 343 times 2 is. And so I get 343 times 2 is going to give me a negative 686. 343 times 3 is, let's make sure I'm not missing a negative in here. Negative 1029 minus 343, 6n squared. Over here, I've got negative 6 times 49 plus 49. So 6 times 49 is 294. So that is a negative 245 times n, which is going to be n. Negative 245 times 1 is going to be negative 245 all over to n. And then over here, we have, let's see, that's negative 63 plus 21 plus 42. Ooh, our first break. This is plus 0, so we're not worried about that at all. That term completely cancels out. I'm only really dealing with these two. We're very happy about that. So I have a 6n squared, which means I just need to multiply by 3n. Okay, so negative 245. 245 times 3 is going to give me 735. Awesome. All of this is all over a 6n squared. And then I'm going to go through. I have n squared, hope. Let's not do that. Let's not do that. N and n. Okay. So my n squared's negative 686 minus 735. So 686 and 735 are going to give me 1421. I have both negatives. 1029 and 735 are going to give me 1764. Awesome. Each over 6n squared. Okay. What we know is that reduce, no reduction. And this is the last step where my limit still exists before I plug it in. Now at the next step, I go ahead and I plug in that limit. So I have negative 1421 over 6 minus 1764 over 6 times infinity minus 343 over 6 times infinity times infinity. Both of those reduce down to 0, so I'm really looking at whatever negative 1421 over 6 is. And so let's take a look at what negative 1421 divided by 6 is. 236.83. Okay. So now what we've got is we have everything that we need to solve it. I have, this is my area above the curve. The negative 236.83 is going to give me the area down here. That is a negative area because it exists below the axis. Now I'm going to take the absolute value and I'm going to add these two areas together. So my area is going to be area 1, which is 13.5, plus area 2, which the absolute value of which is going to be 236.83 repeating. And let's see what that gives us. Oh. Okay, so I'm multiplying it times negative 1, so I get a positive value, plus 13.5. 250.3. Boom. Exactly as we wanted. And so if we look over this, this may seem very tedious because you may like working this problem with numbers up front. And that is okay. This was only a 2-section split, but we saw it wasn't too bad. It was 1, 2, 3. Really 2 hard steps and then 1, 2, 3 easy steps, as opposed to several steps working throughout this. If I split this up, and let's say this was, for example, a sine wave. Let's clear this, and let's say sine of x. Now I know sine is repeating, so we can cancel a lot of these out, or we could find one area and repeat it. We would have to find the area, if we're looking from 0 to 10, 1, 2, 3, 4 times. So as opposed to us just doing the work once and then twice, where the numbers would be a little smaller, I'd have to do it 4 times. That would start to add up. So I'd want to get a simplified equation going on to plug in my final values and compute my final answer. But that is it for absolute area. There you go.